So hello everyone. So let us get started. So I will start with data. I'm just again covering some basic things about data, and that will be helpful for beginners also because the session is being recorded. So when we talk about data, the first thing which comes in our mind is a table, Excel table with row and columns. Okay, and where the every row represents a data point, and every column represents some kind of features. So that is a typical kind of data we generally have. We have rows and rows. These are data points and columns, which are features. And typically we have numerical data. There are numbers. So once we have this type of data, then we can carry out many operations on this data. Correct? We can find the average of uh, columns, rows, and all sorts of numerical analysis can be done on this kind of data. But if we look around in our daily life, that not all the data is of that type. You don't have these tables readily available. For example, we deal with uh, voice data, we deal with text data, and we deal with video and all other kind of data, where we may not even have tables at the first place. Then how we go about doing machine learning? Because the machine learning starts with the data. And here the main focus of this session is on text processing or text data or natural language processing. So in this situation, the first task is to convert this text into numerical data, and to be precise, in vectors. Okay, so we covered some part of this vectorization, how we can vectorize text following different schemes. And so today I will give some examples and maybe demos of some of these schemes. And the Jupyter notebooks are available on the course web page, which is on GitHub. You can directly clone that repository. And I mean, if you know how to install a Python package, that is the minimum requirement. Then you can just start running these Jupyter notebook and you can see results yourself. Okay. So what is our game? Our aim is to convert text into vectors. And there are two schemes I will discuss, vectorization schemes. One scheme is called bag of the word scheme, because text is made of tokens or words. Okay. And if we ignore the ordering of these words, we just consider that what are the words coming in on any text. So that scheme will be called bag of words scheme. And second scheme, which is more realistic, will take into account the full ordering of words, like sequence. So what are the most important, I mean, components of any natural language processing task are like semantics and syntax, bare minimum things. I mean, there can be more things. So when we talk about semantics, we mean meaning of the words. Okay. So as I covered in my earlier lecture, that numerical data has value and textual data has meanings. And these values, the numerical values, they are fixed. I mean, we can't debate about them. If something is 5, then it is 5. But that is not the case for the text data. The meanings of text depend on the context. Okay, so it may change with the context. In fact, as we will we'll be discussing here the distributed representation of words. We assume this hypothesis, or we consider this hypothesis, that words take their meanings from their use. Okay, so in the beginning they may not have any meaning, but whenever people use those words, they pick some meaning. Okay, so that's exactly what is generally done in this large language model, and we have a vocabulary, and then we train our model on these, then we start getting meaning. So in the right column, you see that statistical models are there, globe. Okay, or n-gram based models are there. Some of these things are covered in the first lecture. And then we can have term frequency inverse document frequencies. And on that course page, there are enough links for the tutorials which you can further follow. Okay, and the second scheme is of embedding based scheme, the distributed representation of words. Okay, so how we actually get the vector representation of a word. So again, we can consider even the distributed representation also, we can consider just a bag of words, or we can consider a sequence of words. So we will cover both here. So bag of words scheme is easy to model, not very practical, and fails to get semantics and syntax correctly. You can just think about any example. If you just swap the words in any sentence, it may not make any sense at all. Okay, but sequence based they are difficult to model because they need memory. So nth word, what the nth word will come will very much depend on what was before this. Okay, all the previous words, it will depend. So definitely they need memory, and these are complex model, and they follow the actual language model. Okay, and they can pick semantics and syntax correctly. So what we are doing is that when we read a paragraph, let us think about a task of answering question based on some paragraph. So when we are reading a paragraph, we are remembering something. Okay, we are building our knowledge. You can think that about in terms of some vector. Okay, and when our learning is done, then whenever the question comes, we can refer to that vector or that learning, and we get the answer. Okay, and further attention-based model, which we will cover later on, they actually learn that what are the particular words on which we should pay attention. So that will become, and this is the Jupyter notebook. I will run it. So I have put 2-3 examples in the repository, where one is for Globe, where you can basically what you need for Globe is that you need to download one big file, which is put there in the Globe path. If you look at the Jupyter notebook, and once you have it, so there are a few lines of code basically, and the Jupyter, this Globe model, it has a vocabulary that what are the words for which it will have vectors. Okay, and then we can use those vocabulary to find out the vectors or whatever vectors we need for. So it's easy. I will run it, and this is the example what we can get from Globe. That for 4 words like king, queen, man, woman, I gave just these words, and then I got the vector representation of these. And these vector representation, it's just numbers basically. It's a NumPy array, and we can plot them. And once we have 2 vectors, we can find similarities also, cosine similarity and any other distance-based similarity. There is another library, Python library called GenSim. It's again open source library. We just need to install pip install GenSim, and it has many inbuilt model in it. And it can also be used to get vectors for words. There is a lot of technical detail they are given on the page of GenSim, and it's why it is interesting. There are many features of it. It's super fast. It can do streaming processing, means online processing. It can do. It's platform independent, ready to use models in Corpora, and you hardly need to write a Python code less than 10 lines to get a vector for any word. So this is the first part, to get the vector representation of any word. After that, you can do anything with these words. You can do classification, clustering. So here is the example of GenSim. I will run on this notebook, and the same example is shown here, that we can find the cosine similarities also. So this was the one scheme, and second one most common scheme is the embedding based scheme, where we have some text corpus, and we are trying to get the vector representation of the word present in that corpus using some kind of machine learning or training. So most probably it is a supervised training. What I mean is that if you have a set of sentences, 10,000 sentences, you can build a problem that let us predict the last word of every sentence. Okay, so the last word could be the label and remaining word could be just the features. So like in any machine learning exercise, what we are trying to do is that you are trying to map input to output. And the input data is in terms of features, output data maybe in terms of labels, in particularly in classification. So, or you can try to predict that masked word, like in every sentence, you can mask one word. And that word you can put at your label, and rest of the word you can have your input or the features. Okay. By this, so by this scheme, you will be able to understand the vector representation of the worlds. So there are very specific example in Jupyter Notebook, which will make things very clear. Let us look at this example, embedding by supervised learning. Now you have a text corpus. First you do is that you build a vocabulary of it. In English, generally there are 40,000 words which are good enough for any exercise. You build a vocabulary, you assign one ID or integer to every word. So that's a very basic kind of numeric representation. Then you go in another label, which is called the one hot encoding. So one hot encoding means if there are 40,000 words, then every word can be represented by a vector of length 40,000. And only one of the entries will be non-zero, rest will be zero. So that's called one hot encoding, and you can do it yourself in 2 lines of Python code, or you can use any pre-built libraries. So if we have a text, we can get one hot encoding of it easily. But what after that? Because this one hot encoding doesn't have much semantics. If we try to, semantics means if you say three word, good, bad, and best. Okay, and you are trying to find the distance between good and bad and good and best. So semantics will be that any representation where you will find the good and best are very close and good and bad are very far away. So if you can map these words into a space of meanings, then it will be very easy to do the text processing and to make sense of the data. Okay, let me come to this diagram again from the left. You have the 168 dimensional one hot encoding. Let us consider you have a very small problem of only vocabulary 168. Then you can apply a matrix on it. Obviously, you don't know the values of the matrix element, but you initialize them random. And there is always an appropriate matrix which you multiply on this big vector, and you get a small vector which will be dense. Okay, so at this moment, I have not explained how to set the values of this matrix, which map this one hot encoding vectors to dense vectors. So once we get the vector dense vectors, after that everything is as usual. Like if you have done any linear regression or classification exercise, then you know that like this Boston housing data set is there. So what you have is the columns, which are the numbers, features. So then you have the features and you do your usual thing, what you want to do. And what will be interesting is that in neural network, there are layers of neurons, and every neuron has a weight matrix associated with it. And when we do deep learning, we actually learn the weights of these neurons, these weight matrices. So in case of our embedding, we are interested in embedding layer, which is like after one hot encoding, there will be first layer will be embedding layer. So we trained our machine learning model for classification or any other part we want. Once the model is trained, then we have the weights. So from the trained model, we just pick the weights of the embedding layer only. And once we know the weights of the embedding layer, then we have that matrix, embedding matrix, and we can directly get one dense representation of words. So here it is very simple. You all are familiar with matrix notation. So in top, these O vectors are the O is the one hot encoding, and the E matrix is the embedding matrix. You apply embedding matrix on that, and you get the dense vectors. So dimensionality of the one hot encoding vector is n, which can be very large. And dimensionality of the dense vector is m, which is around 300 or whatever you prefer to use. And the matrix will be some rectangular matrix, appropriate rectangular matrix. So all the notations are clear here. Okay, but how we will do it? Training, initialize embedding matrix to random values. That's the first thing you do. Compute dense vector for the inputs, applying these weight matrices, and then map dense input to output, whatever ML model you have, and then update the weights, embedding matrix elements using backpropagation algorithm as we do. So here I close this presentation. Yeah, so any question?
So that we like dense vector, how we know like
How we know
is we are training model, we took any random embedding vector. We are having one hot also with us. So how we train?
Yeah, so what we okay, look at we have the input data, input vectors. Now input vector will be these dense vector, not the one hot encoding vector. Okay, these are the input vector. Finally, they will be mapped to some output.
That output what
it may be classification.
It will depend upon the task.
Yeah, it will depend on that. So what we do, for example, if we have image classification task. Okay, so every image is mapped to one of the categories. If we have 4 categories, and we tune these weights such that we correctly predict the category or the class by using an algorithm called backpropagation. So backpropagation, it's a gradient-based approach. We have a loss function. So that sits at the core of machine learning algorithm. Basically, you try to find the misfit, take the gradient, and use that gradient to update the weights.
So we are having input as a one hot. Then we'll have one embedding. That will multiply and give dense vector.
Yes.
Where we are applying ML.
Yes, yes. After that, everything usual. I will show the Jupyter notebook. Any other question up to this point? So let me go to the Jupyter. So here is the repository. I think you can see. So this is the wall-to-back using Globe. Okay, and this is wall-to-back using GenSim. Let me click on it. So it's on local Jupyter notebook. So let me run it. So I have taken this set of words, and the first thing I do is the tokenizer, and that tokenizer actually create a dictionary. And then here, what I am doing is I am creating a Python Panda data frame, where the data frame columns will be the dimensions, embedding dimensions. So this embedding dimension is here 50. So every word will be represented by a 50-dimensional vector. And then I arrange these things such that here it is a tokenizer is not defined. I think there is some issue with this, but I will show the vectors. So that is one scheme. Somehow it has some dependency, and think I am not tokenizer read not defined. I will fix this thing. Okay. And then is the GenSim. The similar approach is here. The same words I use. I hope it runs. Because these are large data files. This one. So you can practice with it. Just get most probably this thing was not running because I forgot to switch the environment, virtual environment. So now I come to the part this bag of word embedding. Where instruction I have written, the words tokens can be converted to IDs on the basis of vocabulary, and each sentence can be written in terms of list of IDs. That's the step one. The size of the vocabulary on the number of token to keep is important parameter, that how big your vocabulary should be. It is better to ignore words which have very less count. So we do that frequency distribution also. And then we also need to define the length of sentence. Like if some of the sentences are very long, some are very short, so better to have some intermediate, and we may need padding also. So here it is. If you are familiar with TensorFlow Keras, here is the program. So first thing I have taken this data, and all the data set I am showing in this session are posted on my Kaggle page. You go there and you will find this. You can download them in CSV file. So I read this data file, okay, and then what I do here, let me go one by one. I read the data. This is the main program data. Then I build a corpus, collapsing all the text. Then vocabulary is built with using this function build vocabulary. It is also provided in the same repository. It returns me a data frame, vocabulary data frame, which has 3 columns. The first column is the ID. Second column is the name of token. Third column is the how many times that word comes in the corpus. I use that count to make sure that I am only considering words which have high frequency. And in particular case, I don't consider any word which has less than 10 occurrences. So that limits my vocabulary size up to 25,000. Here, now this is a very common text-to-vector. So before I actually pass these text to embedding layer, I need to replace all the words by their IDs. Even this model, I don't need any one hot encoding because that is taken care by embedding layer itself. What I need to do is that if there is like the sky is blue, there is a sentence the sky is blue. So in place of giving the sky is blue, I give the ID of the sky and blue, like 37, 298, and 835, something this. So once my data is prepared, and output will be labels. It's IMDb movie data set where the label will be 0 or 1, whether it's positive review or negative review. And the input vectors will be numeric vector, padded numeric vector. And the model is here. So input model 100, let us look what is the sequence length. So I consider all the sequence up to length 100. And if a sequence is smaller, I pad it. And if it's bigger, I truncate it. Here is the logic for that. And this is the model. Now it's a neural network model. The top layer model is an input layer. It can have as many data points you want, but every data point should be 100 sequence of vector of 100. After that, here is the embedding layer, and you can compute this with pencil and paper that why this number should be like this one. So it's a rectangular matrix. And then again, when you are multiplying that one hot encoding matrix vector with the embedding matrix, you have to add bias also. So if you consider bias plus that, using these number, you can come up with this number. So once you are comfortable in getting these number with your calculation, that means you have good understanding of neural network. So that is one of the benchmarks, basically, how whether one understand neural network or not, that just give the architecture and one should be able to compute the weights, number of weights. Then the training happen. Let me see if it runs.
In above case, there is embedding is converted into 60 dimension vector from 100 to.
Yes. Yeah, it's running. So you can see that. I think this is the most important part, and it should be clear to everyone. So that is it sits at the heart of all this exercise. In the beginning, also when I was learning, I was not sure about how these numbers are coming. So one hot encoding vector, then there is an embedding matrix, and it gives us dense vector. And after that, in this case, this is really a simple neural network with hardly one layer, input layer. Anyway, it will not be counted as a layer because it does not have any weights. So the first layer in neural network is just for consuming the input. If your input is 10 dimensional, then you always have 10 neurons in the first layer. That every neuron will take one input, one component of the vector. Just it is without multiplying or anything. So you see that it doesn't have any parameter. And after that, there is an embedding matrix. Every neuron will have it in this case and will convert that into, and this is the output, then dense layer. After that, we get the 100 and 2. And finally, we get the none and 2. None means, I mean, as many data points as you have. 2 means just 2. So finally, our this 100 dimensional vector is mapped to a 2-dimensional vector. And from these this 2-dimensional vector, we can predict the class. If the first component is bigger, then we say the class is 0. If first component is smaller, then we say the class is 1. So we apply something called softmax. So you can see that training is happening here. And the matrices are the accuracy and loss. So it is good that we expect in any machine learning exercise, the loss should be decreasing. Loss should be falling with the training. Because loss represent the mismatch between what is predicted and what is the ground truth. So here it is. Again, thing is that there are two parts of the data. One part is the training data and another is the validation data. So in any case, for training data, loss will fall, accuracy will improve when the training happens. But that may not happen with the validation data. So validation data should also, if the validation for the validation data, the loss is not falling, accuracy is not improving, then that means the model is not generalized. So we need to fix it and we need to something. So here we don't see much improvement in accuracy and loss for the validation because it's a toy example where we have a far bigger vocabulary than the data set I have. So in order to satisfy these 25,000 words, I will need a good amount of data. And more cleaning will be needed. So any question up to this particularly?
Right, 100 into 60 is, can you show calculation?
Yeah, 100 into 60. Let me, 60 is the dimensions, latent dimensions of embedding vector. It's a parameter. We can give whatever we wish. It's a hyperparameter.
Its input is 100, then output after embedding lights also 100.
100 into 60. So what will happen that, now think about that, you have a 100 dimensional vector which will have numbers, integers, and the value of these integer will be from 0 to the size of walkable ring. Okay. Now every number will be mapped to a 6-dimensional vector. Yes, matrix multiplication. And then you get this matrix of 100 cross 60. Bias also that either you add it explicitly, okay, or you in matrix you have one extra column to take into account. I mean, I can show that separately that it is possible when you write Wx plus b, where W is a matrix and B is a vector, to absorb that B also in W. So that can be done.
Embedding layer can be rectangular, like it's not a square.
No, it will not be square. Embedding matrix will not be square. Otherwise, we will not get the benefit of dimension getting reduced. It's possible only when, yeah. Bias is also a not hyperparameter, it's a weight, it's a part of weight. So this architecture takes care of that. If you want to add anything extra from your side, so before giving data to the model, you can just add whatever you want. Oh, yes, yes. Yes, we can do the same exercise here also. It will be a complex, but because that was
Embedding layer size 100 cross 60.
yes, you are right. You no, sorry, embedding matrix will not be 100 into vocabulary size. Okay, multiplies by the latent dimensions. That is the exact answer.
What is latent dimensions?
Latent dimensions is 60. Okay, you can let us check in case you are okay. This is 25,000 vocabulary. Okay, so I guess if you multiply this 25,000 and all these number, you may get something like this. Okay, this number. So that's it, just exercise, just see if that is correct, because it must have vocabulary. There should be effect of vocabulary size on these parameters. If you increase the vocabulary size, this number will change. If you change the latent dimension, this number will change. So it depends on three things.
So embedding layer matrix size is 25,000 into 60.
Yes, yes, that's correct. That's correct. So you see here, for the training part, the loss has perfectly come down as it should be, and the accuracy has gone up as expected. But that did not happen much with the validation part. Okay, so that means the model is not getting generalized sufficiently. It is doing overfitting. But anyway, that I mean here our goal was, yeah. Yeah.
So input is 100. Embedding matrix is 25,000 into 60. So
can we just calculate, anyone just write this number?
Let us multiply our input layer, it will give 160 dimension. So next dense layer, why is the 100 cross 2?
Okay, then we have one more layer.
That
so we have, otherwise our answer will be, we need finally it 2-dimensional vector.
After 60, we are again applying some 100.
Yes, we are again applying a neural network layer of appropriate size, okay, which will some sort of eat some of these extra components.
So here in main layer we have two component types, one for that conversion and another for converting to 100.
Yes, but since we are interested only in embedding, so here actually we don't care after that what happened. We will just pick here.
Most of time I see like all the dimension from above is connected to down or down. So I'm not getting from 60 how it's going 100.
How 60 is going 100? See, there are these parameters also here. Okay, so if you if you write a proper matrix multiplication, so it will add up. Okay, we can take this offline. Okay, but it's good to scrutinize how things are happening. As I mentioned that here our goal is embedding. So we will not look down than this embedding. And here it writes a trend model in a file. What it writes a vocabulary.csv and it write a trend model. Where is the trend model is here? Something called model checkpoint. So it will write the model.sdf file. So I will show you that, but before that, once the trend model is dumped as a file, but how to do word2vec from that model? That's what I'm going to show. So I have one Jupyter notebook. It's called word2vec embedding. So what it does, it reads that model. The first thing, load model, it reads, and from that model, it reads this particular layer. So there are stacks of neural network layer. So here what we are doing, the input layer, we are creating ourselves. We have an input layer and we are pulling this embedding layer from the trend model and we are putting that thing under that input layer. And then we have a very small model, just 2 layers. So input layer we are creating here that I want to make sure it does not have any weight parameter or the fitting parameter. And we are pulling that trend embedding layer and we are attaching them and creating a model which has the input data, this first layer, and output data, second layer, and we are calling it inference model. Now we have this model ready for the inference part. We just apply any word vector which is in terms of IDs on this model and it will give me vector. So, and one more thing is that from the trend model, I need 2 things. I need the vocabulary also to map the words to IDs. Because when I get the new text, that is always the case when you get the test data. Firstly, I need to use the same IDs. Otherwise, there will be problem. So whenever you get a pre-trained model, either from Hugging Face and various places, the first thing you should look for the tokenization and IDs. And you should use only that tokenization. Like Hugging Face, there are 2-3 models. You can't do this thing that you use tokenization from somewhere else and model from something else. That would be problematic. So, and then once I have this model, inference model, it's a very simple model, and I can write a method here. Just it will take text as input, and then it will create vector by using this predict method. So, okay, so when I read the full trend model, this was the model, actual model. Just to check, I want to make sure that my inference module can read the model. And from that, I cut down this small model, inference model. And there were these number of parameters in that model. And all these parameters were now pre-trained. I can apply this and I can get these vectors. You can see that here, this is the example, word2vec CSV file, and I get this vector. Okay, let me show this thing. So So in this file, I have all the vectors like from globe. I get these vectors. When I ran that globe module, it dumps the vectors here. And this is the world vector for this embedding model. You can see that. So the is represented by this vector, this 6-dimensional vector. So I have vectors for all the words in my vocabulary. So once I have this number, you can note this is the number, these many words I was using. And yeah, and trained model was here because here our task was not discuss much of neural network thing, but the embedding. So I think this idea is, I mean, it has gone to everyone that how we can get vector representation from the training of a neural network. So it is called transfer learning. So we may train model for something else, and we can use the trained model for something else. Like BALT model, it was trained for masked token. So you mask certain tokens in between, and you try to predict those words. So since it's a highly technical stuff, so I have put sufficient material on the GitHub page where you can go through. I understand that particularly in order to understand this concept, there are 2-3 core concepts you need to understand. One thing is called maximum likelihood method or parameter estimation or chi-square minimization. Second concept you need to understand is the back propagation, which is a very famous machine learning algorithm. Without back propagation, I think machine learning will be difficult to understand. And if you go down here, I have put a lot of stuff here. All the data is put on my Kaggle page. Mathematical background, linear algebra, and some of these popular article. Some of the technical thing I have put. So I have given links of 2 books here. One is called Data Science and Machine Learning, Mathematical Statistical Methods. If you just click on that, you will get the PDF of this book. And there is the Mathematics for Machine Learning. So that is more than enough mathematical background you need. So I am taking these lectures, I mean, rarely, so that people have enough time to check the content. Otherwise, there is no point in, and the course, every session is quite rich. This is the extended part of the first session I have taken, and you can see the content I have put here. The presentation will be put here, video will be put here, codes, which is a full-fledged repository. And these are the key papers in case someone want to go deeper into the things. So these are the very important paper you can check. Many of them have citation in 1,000 and 100,000. Some very important paper. This is a book which is online available. It's some kind of Bible for text and speech processing. I have put some learning word embedding, some tutorial here. And here I have put one very advanced topic. I put because I worked on this project some time back, that why only convert text to vector? Why not code to vec? I was working on a project where you have a GitHub repository and you have a GitHub commits. So GitHub commits have commit message and the green part of the code and red part of the code. Okay, so why not train machine learning model on the code itself? So there were many challenges, like code is not plain text. So we converted it into something called abstract syntax tree or AST. It's a highly technical thing, but no need to worry. You can just check this paper if you are if you really like to understand challenging stuff, you can read this paper, that how code is converted into actually vectors. Yeah, it's possible. People have done it. So it's already there.
It is based on GitHub Copilot.
Yeah, absolutely, absolutely. So, and not only that, actually, I was invited to give a course on this topic in 2020. In Italy, there was a big meeting called Big Date, and I have put my course here. So I linked that course also here. So you can see that the name of course was Big Code. So this course was given in this meeting. I prepared a set of 4 lectures, and all the codes and the presentations are available here. In lectures also there are PPT there. So everything is linked there. I